Hello students, right here again today. We got practice problems for section 5.1. Should be checking your answers. Already completed these problems. You can ensure you're doing them correctly. Number one, we got a helium neon laser emits light with a wavelength of 633 nanometers. So, our wavelength. Wavelength is 633 nanometers. And we want to know what the frequency is. It's nu. So our basic formula is speed of light equals lambda nu, frequency times wavelength. We want to find frequency. It's going to be speed of light divided by wavelength. So equals speed of light, you should have memorized by now, 3.00 times 10 to the 8 meters per second. We want to divide that by 633 nanometers. We need to change from nanometers to meters, and 1 meter, nano. There is micros a million, nanos a billion, picos a trillion, so a billion nanometers in a meter. Billion would be 10 to the 9th. Meters divide out meters, nanometers. Oops, got to write that up there. Divide out nanometers. Put our 10 to the 9th, 10 to the 8th together. We get a 10 to the 17th. Get rid of those. We do a little division here. So calculator, we take a 3 divided by 633. And we get, and I get to keep 3 sig figs here. So I get 0.00. And I need 3 sig figs, 474 times 10 to the 17th. We want to adjust that to proper scientific notation. So I take my decimal, I'm going to slide it over 3 spots. 4.74. I made this number bigger. So that means I need to make the exponent smaller, and it's going to cut down by 3 spots. So cut it down by 3. 10 to the 14th. And we're left with here with the second down in the bottom. So that's a per second, which is a hertz. So 10 to the 14th hertz. 7.47 times 10 to the 14th hertz. This time, what's the wavelength of a frequency with a frequency up? Okay, so this time we want to know wavelength. We've got our frequency. So our formula again is C equals lambda nu. We're trying to find lambda. Lambda equals C divided by nu. So the C, one more time, is 3.00 times 10 to the 8 meters per second, divided by the frequency, which was 4.80 times 10 to the 17th hertz. You can get rid of that hertz, move it up here as a second. And the seconds divide out, and we're left with meters, which is what we want. We're going to get us a real tiny little frequency here. We got an 8 up here, got a 17 down here, so I subtract those, and I'll get 10 to the 8 minus 17 is negative 9. Now we do our division. We got 3 divided by 4. 0.8 equals 0.625 times 10 to the negative 9th meters. Adjusted into scientific notation, sig figs, we get a kit 3, which is what we ended up with on the calculator. So 6.25 made this number bigger, make this one smaller, which would be negative 10 meters is our wavelength. And here we're given the frequency, and we want to know the wavelength. So, base formula again, C equals lambda nu. This time we're trying to find lambda equals C over V, or nu. So lambda equals 3.00 times 10 to the 8th meters per second. Dividing it by 98.5 megahertz. I'm just going to write this 98.5 times mega means million. That would be 10 to the 6th hertz. Do that conversion right away. Now hertz, you can switch to second on the other level because hertz just means per second. Seconds divide out. We end up with a 10 to the second as we reduce down the 10 to the 8th and the 10 to the 6th. And we divide the 3 divided by 98.5. And we get 0.03. Now I got to keep the 3 sig figs again. So I'm going to need a 0.5 times 10 to the second. Now, 10 to the second, pretty small. I'm just going to think about just moving my decimal point 2 spots to get rid of that. And that gives me 3.05 meters for my wavelength. Pretty good size wave. Then calculate the energy of a gamma ray photon whose frequency is. The energy, we have the formula energy of a photon, or energy of a quantum, you're only talking about the same thing, is h nu, h Planck's constant. So we want to calculate the energy, so don't have to rearrange the formula. Planck's constant, don't have to memorize this one, I will always give this one to you. If you happen to memorize it, that's good. Some of you probably have got it memorized. Anything you do memorize is always good. And then times frequency was 5.02 times 10 to the 20th hertz. Hertz becomes second down here, which divides out that second. Leaving us joules, right unit for energy. And we'll go ahead and multiply the 6.626 times 5.02. And we get to keep 3 sig figs. And that would be 33.3 times 10 to the, we get to add the exponents together. And negative 34 and 20 is negative 14 joules. Move our decimal back 1 spot to get it in proper scientific notation. We get 3.33. I made this one smaller, so I want to make this one bigger, which would be a negative 13 joules. Don't look like a very good 13. There we go. So what's the difference between the energy between the photon of a violet light with frequency of and a red light with frequency of? We could, and it'd be a good way to do it, calculate the energy of one, calculate the energy of the other. If you did it this way, that's a really good way to do it. And then subtract. But I'm going to show you another way to do it. So, what we want to do is take, I'm just going to call it E1. Actually, I'm going to say E2 minus E1. Energy 1 minus the energy of the other. So that means we're taking H nu 1 minus H nu 2. That basic algebra property, we can distribute that H out or factor it out, and we get D1 minus V2. Here we're just applying a little bit of algebra skills you should have learned by now. You need to do algebra 1, algebra 2. So, and then this allows us to subtract and then multiply, and it ends up shortening our work down a little bit. So many times you can shorten it out, but a straightforward method of calculating one, calculating the other, and then subtracting. Good. So now I just need to subtract the 2. So I'm just going to take the bigger one minus the smaller one. So we got 6.8 times 10 to the 14th hertz minus 4.3 times 10 to the 14th hertz. Now, because these were always the same power, same units, that's what we got when we want to subtract. And I get a 5 and a 2, get 2.5. And now I go to HV. So the H, again, was 6.626 times 10 to the negative 34 joule seconds. And we want to multiply that by 2.5 times 10 to the 14th hertz. Hertz second. You can automatically write that as a per second, and you don't. But here I'll always write it down and then change it just to remind you what you need to be doing. So now I do a 6.626 times 2.5 equals, and this time I'm going to keep 2 sig figs, which is going to be 17 times 10 to the add the exponents, and we get negative 20. Do a little adjusting. I want to bring my decimal back one spot to get 1.7. I made this number smaller. I'm going to make the other one bigger. Times 10 to the negative 19th joules is the difference. Well, a little less typing things into your calculator with this method. A little more thought on how to accomplish it. But as I said, if you would have went and calculated one energy, calculated the second energy, subtracted them, should have got the same answer. And that would have been an excellent way to do it too. Another energy problem. This time though they give us the wavelength. Gave us the wavelength. That means we got a little more work to do. So we're going to bring both our formulas together. We know the energy of a photon. Again, if it says energy of photon, energy of quantum, we're talking about the same thing. Just looking at it in a little bit different way, but for all of our purposes, same thing. H nu. And then earlier we used the formula C equals lambda nu. So what I'm going to do is rearrange this formula into nu equals c over lambda, and then we substitute this in place of that. So our new formula becomes energy of a photon equals h times c over lambda. Now, we could have went through and calculated the frequency using this formula, then substitute that number in, and that would work. But I always like to put it in one formula, just take all our calculations at one time. So it equals h, which we've just been using, 6.626 times 10 to the negative 34th joule seconds, times c, which is 3.00, times 10 to the 8th meters per second, and then we want to divide it by the wavelength, which is 49.0 nanometers. Now the seconds are going to divide out the second. Now I need those nanometers to divide out, and I'm running out of room here on my whiteboard, so I'm going to extend it down here. And we know there's 1 meter, nano, again, I mentioned earlier in this video, that's a billion. Remember, micro, million, nano, billionth, and pico, trillionth. So a meter is 10 to the 9th nanometers. Then the meter is going to divide out the meters, and nanometer is going to divide out the nanometers. Now I'm going to take this 10 to the 9th and just bring it up here so I don't lose track of it. Okay, so we're down, just think, yeah, we got a whole, I have all of our 10 to the stuff are on top, and what right over here on the 3.00 times 10 to the 8th, forgot to write my 10 in there. Okay, now I'm going to put the 8 and the 9 together. That just becomes a 17. And then this negative 34 and the 17 ends up being 10 to the negative 17th. And now I can do my calculations, which is on the calculator, 6.626 times 3 divided by 49 equals, and it looks like I get to keep 3 sig figs. In this case, that's going to be 0.406. Little bit of adjusting here. Move my decimal one spot, and I get 4.06. Made this bigger. That means I got to make my exponent smaller, which kicks me up to a 10, or down to a 10 to negative 18 joule is our energy in a photon of this ultraviolet light. Remember, your energies, if you're talking energy of a photon or energy of quantum, always should be really, really, really small numbers. So there's a little bit of calculations. Need to be able to do calculations like this as we move into our quiz at the end of the chapter. So that's it for now.